So coming to our last problem of cell balanced momentum. So this problem we can see that we have three fluids flowing on a horizontal plates. This is the top plate, this is the bottom plate, and we have the three fluid of fluid 1, fluid 2, fluid 3, which are invisible to each other, and they are flowing in horizontal direction. So first of all, we read the question. We have given the length of the top length of the plates are zero point 0.7 and width of the plate as zero point 0.7 that was separated by 3 into 10 to the power minus 3 meter. The distance between the two plates is 3 into 10 to the power minus 3 meter as shown in this figure, and all three fluids share the equal flow area. All the fluids have the same area as they have the same length, same width, so they have and the same thickness B. So all have the same area, and their densities are like rho 1 equal to 800, rho 2 equal to 667, rho 3 equal to 569, and the kinematic viscosities are mu1 v1 rho 1 sorry, this is the viscosities are 1.5 into 10 to the power minus 4, 1.76 into 10 to the power minus 4, and 1.25 into 10 to the power minus 4. These are three viscosities of the air. And the pressure difference between the fluid, the pressure difference, this point is taken as P naught and this is as PL at length L. The difference between these points are this point are given as 4 into 10 to the power 3 Pascal. Basically, this is the pressure difference between the two ends of the flowing direction. So these are all the things are given in a SI unit, and we have to derive the expression for flux profile and velocity profile for the problem, and also you have to find the mass flow rate for all these for all three phases. So before starting the question, first of all we write down all the given things: densities rho 1, rho 2, rho 3, b1, b2, kinematic, this is a viscosity, kinematic viscosities, this is nu 1, nu 2, nu 3, and pressure difference is delta p. So before starting, first of all write the assumptions. As we have mentioned that the fluid are moving in a horizontal direction, as this is a laminar flow which is basically a 1D flow that is taking place in a z direction. This direction is a z direction. We're taking our coordinate system as Cartesian xyz, in which our origin is at this point, bottom plate on left hand side. This direction is z direction, this direction is x direction, and the perpendicular to z and x direction, that is y direction, that is inside the our face. So as Bz is not equal to 0, we have given the question Vy equal to 0, Bx equal to 0. These velocities are need to be 0 as there is a 1D flow. So the 1D flow is take place that is in a z direction. So Bx component, Vy component must be 0. And there is a Bz is not function of z and y, as we have to neglect the end effects, and the fluid is incompressible. So there is a no variation of the jet velocity in z direction and y direction. There is a variation take place in x direction. Bz is a function of fx. It means when you move this side, we have variation of our jet velocity in this direction. There is a velocity 0, there is some velocity, this is going on, and at here some maximum velocity will be happening, and at that point there is again the velocity is 0, and we have to take the assumption not, these are the boundary conditions, as we have assumed that flux continuity equation is follow flux continuity equation. So coming to the here, that momentum due to them, as here bx and by is 0, so the momentum due to this velocity component is must be 0, as there is a no velocity in x direction, no velocity in y direction, so there is a no momentum caused by these velocities, as we have 9 velocity component, 9 momentum component: phi xx, phi yx, phi zx, phi xy, phi yy, phi zy, phi xz, phi yz, phi zz, phi xz, that is p plus rho bx square plus tau xx. As velocity in x direction is 0, tau xx is 0, so there is a no net momentum. Phi x will be 0 as Vy is 0. tau ix is 0. Similarly, for all these six equations, we have net momentum is equal to 0. So we have remaining with only three momentum equation. That was phi xz, phi yz, phi zz. Phi xz, z momentum, jet velocity in x direction. Basically, this means that jet momentum transferred in x direction. This is written as rho bx bz plus tau xz. As bx is 0, this term will be 0. This term will be remaining, and phi yz. In this also vy is 0, so this term will be 0, and tau yz, which we write here that minus mu into dvy by dz plus dpz by dy. There is a no velocity in y direction, so this will be 0, and there is a no change of z velocity in y direction. This term will also 0, so we get phi yz equal to 0, and phi zz. There is a some pressure P and rho bz. There is a some velocity of bz and tau z. This is 0, as there is a no change of jet velocity, bz velocity in z direction. So only we are remaining this two term P plus rho bz square. This thing. So from all nine equations, only we have two equations which going to give us a momentum flux. And this equation we write as a phi xz, that is equation 10 and equation 11. So writing the cell momentum balance. So first of all, we have to need to take a cell, a small differential element. As the variation take place in x direction, this direction, so we take a small differential element in this direction. That is with delta, thickness of delta x, length L, and width W. This. So if we balance, we do the cell balance here. First of all, we know that what is the cell balance. Cell balance is rate of momentum in by convective transport minus rate of momentum out by convective transport plus rate of momentum in by molecular transport minus rate of momentum out by molecular transport plus force of gravity acting on system. So as there is a no horizontal component of gravity in there is no gravity component in horizontal direction, so this term will be 0. We have remaining only four terms these. So writing our cell balance equation, that is first of all see in which direction is the momentum is going. So z momentum in z direction coming from this side and going from here, phi z momentum in z direction is out from this. At z equal to 0, it will be in, and at z equal to L, it will be out. Similarly, z momentum transferred in x direction will be in from this side and leave from this side at a thickness of delta x. So writing our cell balance momentum equation. So first of all, flux we multiply area, and the area will be perpendicular to the momentum. So z momentum in z direction have the perpendicular area that have a length, no, that have a width W and thickness B. Thickness B, there is a we take a small thickness delta x, so W into delta x. This will be perpendicular area to phi zz. So area into phi zz at z equal to 0 minus phi zz at z equal to L plus phi xz this one at x equal to x minus phi xz at x plus delta x into area. For area perpendicular to phi xz component will be L into W. We can imagine this if our shear stress is transferring in this direction, so there will be the particular area is L into W. So putting the values of all this from the above, we have P plus rho bz square into W into delta x, that is the area, and minus P plus rho bz square at z equal to L into W into x plus phi xz x equal to delta x into this area, particular area L into W minus phi xz into L into W at x plus delta x. So we have this equation. There is no gravity component, as there is a no gravity component in horizontal direction. So as rho b z square will be same at z equal to 0 at z equal to L. As there is a incompressible fluid, density will be not going to change, and velocity bz Vz is also not changing, as Vz is not a function of z, z direction. So we cancel out these two terms. We remaining with p at z equal to 0 minus p at z equal to L into w into x plus phi xz at x and phi xz at x plus delta x. So after equating all the terms that will be cancel out, we get our equation reduced to in this. Further reducing this equation by dividing w into del L into delta x, we get p naught minus dl upon L plus tau xz at x equal to x minus tau xz at x plus delta x upon delta x equal to 0. So this is nothing but this is a different derivative of the tau xz. So we write as d by dx of tau xz equal to delta p by a, this thing. So for fluid 1, first of all you have to integrate this equation in respect to x. We get tau 1 xz equal to delta p upon lx plus c1. Similarly for fluid 2, fluid 3. This is for fluid 2, this is for fluid 3. We write 13th equation, 14th equation, 15th equation. So we have three constants c1, c2 and c3. We need to find all these constant. So we have to use our boundary conditions. So first boundary condition is that at x equal to b, plus continuity equation. As x equal to b, this thing at x equal to b here, the shear stress due to the fluid 1 is equal to the shear stress due to the fluid 2, and the velocity of fluid 1 is same as the velocity of fluid 2. As they are immiscible fluid, they are incompressible, they are flowing in 1D laminar flow, so they have to follow flux continuity equation. So therefore, from flux continuity equation, we have shear stress tau xz1 equal to tau xz2. So writing these and cancelling both term delta PL into B by delta PL into B, we get C1 equal to C2. Similarly, applying boundary condition 2 at x equal to 2b. Here also we have flux continuity equation. So tau xz2 equal to tau xz3. We get C2 equal to C3. So C1 equal to C2 equal to C3. We take all three constant as a single constant C. So our equation reduced to tau xz equal to delta P upon L into x plus C. And again as tau xz equal to minus mu dBz by dx. So integrating again, we get our velocity equation as vz1 equal to minus delta p upon mu1l into x square by 2 minus c1x upon mu1 plus c21. Similarly for fluid 2, fluid 3, we get the equation 14, 15, 16, 16th. So as we see above that, tau xz equal to tau xz1 equal to tau xz2, tau xz3 all have the same shear stress. So as we have same shear stress, we have same viscosity. When we find our viscosity mu1, which is nothing is equal to mu1 into rho 1, that is 0.1, mu2 is 0.2, 0.1, mu3 is 0.1. All three have same viscosity, all three have the same shear stress, so all three have the same velocity equation, same velocity profile. But before concluding, we are going to further solve this. All three have the same viscosity and same shear stress variation. So first of all, at x equal to 0, bz1 equal to 0, at x equal to 0, bz1 equal to 0, as there is a no slip boundary condition, as the bottom plate is not moving. So the fluid attached to the bottom plate is also not moving. So we can assume that velocity of that fluid is 0. So at x equal to 0, bz1 equal to 0. So from this we find that c21 equal to 0. Here you can see that if we put x equal to 0, x equal to 0, bz equal to 0, so c21 equal to 0. So similarly for at x equal to 3, again no slip boundary condition, as the fluid attached to the top plate is also not moving, that is a no slip boundary condition. So our equation 16th, this equation bz3 equation, when you put the value of x equal to 3v and viscosity, we get the relation between c1 2 and c2 3, that will be C23 equal to 0.257 plus 0.03 C1. That is equation 18th. And now at x equal to b, that is 0.001. We have the flux continuity equation. So if you have a flux continuity equation, flux continuity will have take place. So at that point, bxz1 equal to bxz2, as there is a flux continuity take place. So velocity object component in x direction due to the fluid 1 equal to velocity of jet component in x direction due to velocity due to the fluid. Velocity of jet component in x direction due to fluid 2 will be same. These things, these both. So balancing these equation 14th and 15th. This equation, that is, we have seen that at x equal to b, these both term are cancel out as viscosity is same for both, and x is also same for both. So both term are cancel out, and this term also cancel out as x is same for both, viscosity is same for both. We get that C21 equal to C22. We get that C21 equal to C22. Okay, and again we apply flux continuity equation for x equal to 2b. X equal to 2b. When we take x equal to 2b here 0.002, again flux continuity. So velocity bxz2 equal to bxz3. So again evaluating 15th and 16th equation, we get C2 second equal to C2 third. So from the equation 19th and 20, we get C2 equal to C21 equal to C22 equal to C23, and all fluid having same velocity profile, which is given by. So from this we conclude that all the fluid have the same velocity profile, same velocity equation, that is given by equation 21. Dz equal to minus delta p upon mu l into x square 2 minus c1x upon mu plus c2. Now applying boundary condition, this is the required thing, and now we are going to further solve the question. Now applying boundary condition at x equal to 0. At x equal to 0, we apply no slip boundary condition. Vz will be 0. So C2 will be 0. If you put x equal to 0, Vz is 0, x equal to 0, we get C2 equal to 0. So our velocity equation will be reduced. Our velocity equation will be reduced to this. Vz equal to minus delta p upon mu l into x square by 2 minus c1x by mu. Again at x equal to 3b. Vz equal to 0. No slip. This is a no slip boundary condition. As top plate is not move, so the fluid attached to that is also not moving. So from this boundary condition, if we put the values of x equal to 3v and value of mu delta p, we get the some value of c1, that is equal to minus 8.571. So putting the value of c1 c2, so putting the value of c1 c2 in the equation 21, we get our velocity equation as like Vz equal to minus delta p x square upon 2 into mu l plus 8.571 into x upon mu. And in question we have asked about the location of maximum velocity. So maximum velocity occur at the when the slope of velocity equation is 0. That is dvz by dx equal to 0. Slope of tangent will be 0. So when you differentiate this equation, we get the value of x as 1.5 10 to the power minus 3 mm, 1.5. This is in the middle of the both plate here, and the middle of the both plate. So location of the maximum velocity is at x equal to 0.5 mm, which is the mid in the both plate. And now we have to find our equation for shear stress. So as the maximum velocity, at maximum velocity we have tau xz equal to 0, and our equation for tau xz is delta p upon L into x plus c1. So value of c1 is minus 8.57. So we get our equation for shear stress as this. After further substituting the values and calculation, we get tau xz equal to 5714.28x minus 8.57. So as maximum momentum flux magnitude occur at where velocity will be 0. So velocity will be 0 at 2 points. First point is x equal to 0, and then second point is x equal to 3v. So our maximum momentum flux is acting on x equal to 3v, x equal to 0. As we have to ask magnitude, so both point will be take place. If they are asked about direction, negative sign, so x equal to 0, they have negative sign, we have negative sign of flux, and x equal to 3v, we have positive sign of flux. So if we put the value of x equal to 3v, we get our tau xz max equal to 8.571 kg meter per second square. So coming to our last part of the question, in which we have to ask the mass flow rate of all the three fluid. So before finding this, we have to find the average velocity, and we know that the average velocity equation is Vz equal to integration of Vz into dx perpendicular area dx into dy upon double integration of dx to dy, this thing. So as there is no variation take place in y direction, so we ignore the y direction as it will be cancelled out from numerator and denominator. So we get our average velocity for Vz1 is 0.033. We take our limit from 0 to 0.001, and this is a fluid one. Fluid one is only have thickness of b equal to 0.001. So we get Vz1. Similarly for the fluid 2, which is have a thickness from 0.01 to 0.002. So we get Vz2 equal to 0.061. If we put all these things in this equation, similarly we get Vz3 if we integrate from 0.002 to 0.003. So we get the average velocity for all these three fluids, that is Vz1, Vz2, average Vz3. So mass flow rate is equal to density into area into average velocity. As we know that area will be taken as a perpendicular to the velocity. So as our system is moving in z direction, this direction, z direction. So for this direction, we have the perpendicular area that have a width of w, and thickness of b. This I like this thing, w, and this is b. So this is the perpendicular area. If you take this, so we get density into area into average velocity. So we get Wn, mass flow rate for the fluid 1. Density is fluid 1 is 800. Width into thickness. Width that is 0.7 and b 0.001. Average velocity is 0.033. We get mass flow rate for fluid 1 0.01848 kg per second. Similarly, we get W2. There is only two chains. Density will be 6667 and average velocity will be 0.061. We get our mass flow rate for fluid 2 is 0.0284. Similarly, we find for W3 that is 0.01314 kg per second. So these things are asked in our problem, but we add something extra, and we have to further plot the profile of velocity and shear stress. As we see that Bz is a function of x square, so it will be now, so the profile of the velocity is now parabolic nature, and we further find as earlier that maximum velocity apparent of 1.5 mm here, and velocity at the top and bottom plate will be 0. So our velocity profile look like this is the quadrant parabolic, this like this. And for shear stress, as we know that at the maximum velocity we have the shear stress as 0, and shear stress is increasing in the direction of decreasing velocity, and as tau xz is a function of x, this is the x, so our velocity is our shear stress is very linearly, this is a straight line, and here is a 0 shear stress, and there is a maximum shear stress. There is a maximum shear stress in negative direction. So this profile is for shear stress, self stress flux. So we conclude our last question. That's all.